Okay, hello everyone. So in this movie clip, we are going to begin with taking a look at the cross-sectional view of modern NPN, not PNP, NPN bipolar junction transistor structure. So as shown in this figure, let me bring my electronic pen. Okay, so you can find emitter. Yeah, there we go. So this is instead of crystalline silicon, we have used heavily doped polysilicon. Why polysilicon is better than crystalline silicon for BJT for improving the device BJT device performance will be studied soon in the upcoming lecture note. And you can see that the p-type base and n-type collector. So core part of the BJT device has been built in this part. However, there are so many different parts other than core parts. What else do we have? Deep trench, maybe for electrical isolation from away from the other BJT devices, and the sub collector instead of a collector. Why M plus sub collector is necessary? And how come the P plus base is P type, but P plus are adjusted and formed uh, at the sides of the P type base? Why is that? Why P plus polysilicon has been used as a base contact? So and another question is how come the base width is very narrow? And how come the collector region is narrow, but another sub-collector is very thick? And here M plus and contact metal semiconductor contact has been formed for collector electrode. So tons of questions you can raise up. So try to take your own time to answer for your question that you have created. So just for your information, I have listed up a few key features found in modern NPN BJT device structure. Number one is narrow base. So we have already learned why narrow base is necessary, right? So here I'd like to give you the number. The base width, the quasi-neutral base width should be smaller than, narrower than 100 nanometer, okay? And number two is M plus polysilicon emitter instead of crystalline silicon emitter. We will study the technical advantage of using it soon, but herein I would like to give you the number. zero point 0.5 nanometer thick polysilicon emitter has been widely used. Okay, and number three is a self-aligned P plus polysilicon base contact. So here, base contact P plus polysilicon has been. Can you see that here? Yes, self-aligned structure has been well developed. Number four is collector side should be lightly doped. I mean, when we discuss the PNP BJT device, P plus and P minus, that is our optimal doping concentration profile for PNP BJT. So similarly, in NPN BJT device, definitely N plus P N minus. So collector side should be lightly doped to boost up the device performance, emitter efficiency, DC, beta, alpha T value stuff. Number five is architecturally grown sub-collector, which is heavily doped, is required. So here, why this heavily doped architecture of sub-collector is necessary? The sub-collector means this sub-collector is positioned below the N-type collector, and the doping concentration is very heavy. Why is that? Yeah, for reducing R sub C. I mean the collector resistance value itself should be minimized. Okay, and one more thing that I have missed is one of the reasons of adopting lightly adopted collector is if we can have collector doping concentration lower and lower, we are gonna achieve very large early voltage value. Okay. And number 6 is the shallow trenches and deep trenches filled with SiO2 for electrical isolation away from other PJTs. Okay, so deep trench has been widely used, which is quite similar to the shallow trench isolation technique for MOSFET to be isolated away from the other MOSFETs, which is widely used in industry currently. All right, so we have briefly gone over the cross-sectional view of modern NPN BJT structure, and now it's time to take a look at the technical advantages of using polysilicon emitter instead of crystalline silicon emitter. So on the right hand side, you can see the doping concentration along the x direction and emitter base collector. Definitely this NPN BJT is working in active mode. In other words, the emitter base junction is forward biased and the base collector junction is reverse biased. Then, take a look at the depletion layer width. Yeah, definitely emitter junction is narrower than the depletion layer of collector junction. And many holes would be injected into the inside and many electrons would be injected into the base, right? So the excess minority carrier concentration in emitter, which is hole because this is n-type, and equilibriums at thermal equilibrium in the emitter, how much hole concentration has been there. Therefore, this factor is key. And when we draw the excess minority carrier concentration, this slope is critical when it comes to estimating the diffusion current component in the emitter region. So all these physics comes from and is originated from the PN diode theory, right? All right. But here the topic is, what if we are replacing crystalline silicon with polysilicon as shown in here? So this very top portion, right, uh, has been replaced with polysilicon instead of silicon. No, here. Yeah, sorry about that. Let me tell you again. Yeah, take a look at here. This part was originally crystalline silicon, but it is replaced with polysilicon. Then what would be happened in terms of excess minority carrier concentration as a function of x? So as described here, reduce the dPe of x dx at the edge of the emitter depletion region. So go back to this polysilicon, take a look at here. Then we're gonna achieve this less sloppy slope in the emitter side. So since whole current should be continuously flown in emitter, so this diffusion current component should be identical at the interface between polysilicon and crystalline silicon. So from that, we can derive the full equation for excess minority carrier concentration as a function of x, uh, as shown in here. And the key idea is emitter 1 and emitter 2, polysilicon, crystalline silicon, the mobility of electron holes in different materials should be very different. So this factor can be used to boost up the sensitivity of excess hole concentration in emitter. So by modifying this value, we can boost up the gain value beta, right? So beta DC should be much higher for a polysilicon emitter BJT compared against all crystalline emitter BJT. So in industry, polysilicon emitter has been widely adopted in terms of improved beta DC value. Okay, so now let's take a look at the impact of emitter Gummel number with polysilicon emitter. Previously, we defined the Gummel numbers for emitter base collector with the all crystalline silicon BJT. What if we are adopting polysilicon emitter? Then what kind of how to adjust the complicated equation for, or the definition for Gummel number? So previously we have defined the Gummel number for emitter as shown in here. The only thing that different modified is this SPD electron emitter poly and the depletion width in polysilicon emitter. And one more definition is surface recombination velocity. If you estimate the unit for this value, then you're gonna see that centimeter per square. Okay, all right. Just for your information, what if doping concentration is very uniform? Then you can ignore this integration stuff. Then your equation for Gummel number for emitter is very simplified. So take a look at this guy, right? Because of adopting polysilicon emitter, we have a one additional terms. Okay, and the follow-up question is, in the emitter region, we have adopted polysilicon instead of crystalline silicon. Then what if we are adopting very small bandgap material in the base or in the emitter? What kind of benefits can we expect? So going back to the equation for beta value, because we would like to have a much higher beta value in BJT design, take a look at here. What if the same crystalline material has been used for emitter and base? Well, definitely N sub I intrinsic carrier concentration, which is 10 to the 10 per cubic centimeter at room temperature, so they are same. So we have canceled out in all crystalline BJT device. But let's go back to the original equation and think about any uh, missing point or any chance to enhance the beta value. What if NIV is much higher than NIE? What kind of engineering solution can we come up with? Yes, narrow bandgap material can give us much higher N sub I. So for example, silicon, N sub I of silicon, N sub I germanium, that is at room temperature 10 to the 10 per cubic centimeter, but in germanium case, 10 to the 13 per cubic centimeter at the same temperature at 300 Kelvin. So 1000x improvement can be obtained. Then, if this value NIB squared divided by NIE squared, 1000 squared, so that it turns out that 10 to the 6 million times higher. Okay, so theoretically, we may expect million times higher beta value. What if we are using germanium material in the base region? Okay, so to achieve large beta DC, N sub E, emitter doping concentration should be very large, so the bandgap narrowing is very significant, right? So this Ni value should be increased. So because NIE value has been increased, beta DC has been degraded. So to suppress these disadvantages because of the bandgap narrowing event, we can use some not pure silicon material, but some germanium incorporated silicon material in the base. I mean the silicon germanium. What if we are using silicon germanium in the base? Then NIB would be increased, then this degradation would be cancelled out, or even we can overcome this degradation event. Okay, so in industry, they have adopted silicon germanium material in the base. So to improve beta DC value, we can increase the NIB, right? How? Yeah, by using base material, which is non-silicon but silicon germanium material. So SiGe has a smaller bandgap than silicon bandgap, pure silicon materials bandgap energy. So what if the portion germanium, 20% germanium has been included in the silicon, then delta EB bandgap narrowing is about up to zero point 0.1 electron volt. This is good news because we can increase the N sub I value. Okay, so this technique, silicon germanium based material, can allow us to have a very large beta value. Okay, and another advantage has been introduced here. Since we are using a very narrow base material, so the base resistance value has also reduced together, and it would give us a very high early voltage, which is good news to overcome the kind of short channel effect or narrow base width modulation we can overcome by simply adopting a silicon germanium material in the base. So now your BJT has been designed with a polysilicon emitter as well as a silicon germanium material in the base. Then, emitter side is a silicon and the base is a silicon germanium, so which is quite different material. So we can call it a heterojunction instead of a homojunction. When we have studied a PN diode with a pure silicon material, that PN diode has been named as a homogeneous junction diode or homojunction diode. But herein, because we are using a silicon germanium in the base, we can call it heterojunction BJT. So here, heterojunction bipolar transistor. So if I take a first capital letter, HBT, okay? So in industry, to fabricate very high-speed integrated circuit chip, HBT has been widely adopted because it is CMOS fabrication compatible technique, and ZigE has been widely adopted in plain bulk MOSFET technology about 2 decades ago. So maybe when in 2003, Intel Corporation has for the first time has adopted silicon germanium material in the source and drain region for P-type device MOSFET. So silicon germanium is quite familiar and the hands-on experience that the industry has a lot. So this is not a very high uh, barrier. Okay, so the last thing that I would like to teach in this movie clip is can you draw the energy band diagram for all uh, uniform germanium concentration in BJT case? I mean, definitely HBT, but in the BJT, what if germanium concentration is very uniform? Can you draw the band diagram against the conventional BJT, all silicon BJT? Yeah, the black colored one indicates energy band diagram for all silicon BJT, but if I'm adopting a silicon germanium material in the base, take a look at here, the band gap narrowing has been happened, right? Emitter side and base side. So you can see the offset uh, at the heterojunction edge. And the second one shown in here is a linearly graded germanium concentration has been implemented in base. So I mean since the germanium portion has been linearly graded in the base region, the band gap value has been linearly decreased. So what is the technical advantage of using this type of silicon germanium material in the base? Yes, the band banding has been additionally obtained, right? Compare against this guy, take a look at here. Band gap has never been modified, but here the germanium portion has been increased from here to there. So band gap narrowing has been happened a lot, not band gap narrowing, the originally germanium portion has been increased so that the silicon germanium, I mean here silicon germanium is zero point 0.3, here silicon germanium zero point 0.2. Okay, so as the germanium portion has been increased from the edge of the emitter to the edge of the collector, the band gap energy level has been decreased a lot, so that spontaneously the band gap, the band banding has been obtained additionally, so that the built-in electric field has been obtained and achieved more. So this built-in electric field is a good news. Why? The electrons can drifted more because of this built-in electric field. So compare in the case of number A, uniform germanium case, this built-in electric field has not been formed in the base. But what if you can develop your own fabrication recipe to achieve linearly graded germanium concentration in base, then additionally obtain the built-in electric field can help the electrons to be well drifted in the base. Then, emitter efficiency would be increased so that resulting in the higher beta DC value. Okay, so please have your own time to solve this example, and with many numbers are provided, as please do your own hands-on experience. So that's all for the BJT stuff, and I guess charge control model based transit time and stuff are the just a very optional material. So if you have some time, please have your own time to do the self-study. So I guess maybe for your final exam evaluation, I'm going to use the material by slide number 16 in BJT number 3. But just for your information, if you have a time charge control model, base transit time, and others, please take your do self-study. So thank you very much for your attention and see you soon and again in class or in elsewhere. Thank you very much for your attention. Bye bye.